So good afternoon. Welcome to the NPTEL last live discussion on BioMEMS and Microfluidics. I hope I am audible. So it's good afternoon. Welcome to the last live discussion, week 8 live discussion on BioMEMS and Microfluidics. The course instructor for this course is Dr. Shanthanu Bhattacharya, and the live session is handled by myself, Sabareesh Vijayakumar, and I'm the PhD scholar in the Department of Mechanical Engineering at IIT Palakkad. To say about myself, I am the PhD scholar and the PMRF at the Department of Mechanical Engineering at the Harlia campus, and my research area is passive cooling applications. So the main objective of this 1 hour live discussion, as with the previous, is to have a quick recap of the weekly sessions, just a glance through of the weekly sessions. Then we can discuss some important Q&A related to the weekly lectures. Then if there are still any doubts or queries, we can clear that and we can move on. So in the week 8, the main topics discussed were microelectronic fabrication processes, which involves the fabrication of the electronic item, electronic chips, the processes, the integration of them into circuits. What are the processes involved that were discussed? Then comes the fluidic part, which was dealing with the conservation of momentum equation. So as you may know, the three essential equations like conservation of mass, conservation of momentum, and conservation of energy. These are the three fundamental conservation equations associated with any kind of systems that we are under consideration. So in the fluidic part, the conservation of momentum equation was discussed because that becomes the important part of the weekly discussions. Then the microfluidics, which involves the study of the flow through micro channels, which means the channels that are in micro level sizes. Then the different types of flow and the flow through channels discussion. Then the different types of micro mixers or the mixing of the fluids, that is discussed. Then the concept of micro valves and the micro pumps, all such were also discussed. Okay. So I hope I've gone through the weekly lectures, so that will provide a good understanding of the concepts through that. So the micro mixers were one of the few concepts that has been discussed. So what are micro mixers? So it's a microfluidic chip, and it's a set of another micro channels which are etching process is done into a material such as glass, silicon, or polymer such as PDMS for polydimethyl siloxane or etc. So a chip that is etched into a substrate, into a glass or a silicon base. So the channels are created within that chip so as to enable the flow of the fluid, which involves the transport of the microfluid through that channel. So what we can do in this microfluidic mixing is mixing of the several types of fluid. Suppose a fluid 1 is coming and it needs to be mixed with another kind of fluid 2, and if there is another kind of fluid 3, if suppose fluid 1 is water, then another is suppose say another kind of fluid, say for example maybe alcohol or some other kind of medicine or which are used in diagnostics. So we can say some medicinal fluids, something. So if all of them have to be mixed, we are separately creating channels so as to enable the proper mixing of them. and the flow has to be very smooth and connected. So please understand that the connected feature should be enabled. So even the channel dimensions determine the pressure of the fluid flowing through the channel. If the diameter D is more, the pressure inside the channel may decrease. That is less, it may decrease. So if several types of fluids are coming, they have to travel through a particular pressure. Suppose if water is coming, it has to come through a pressure P1. If another fluid comes, then it has to come to a P2. So finally, they have to mix together and flow through the another third channel, say suppose 1, 2, 3. And what is the criteria that it is to be met? If we are to ensure uniform velocity, then the channel diameter should be decided so that uniform velocity will be available at the exit also. So that concept need to be understood. Okay. So you can see here in the figure, in figure 1, there are several kinds of micro mixer types, A, B, C. So you can see in the D figure, you can see the channel size. You can see here, it's in the 1 centimeter. That is the length of that channel. So it's in the very, very less scale. You can see the channel being created inside this so that the fluid can flow. Several, so they will be packed or arranged in such a manner that the mixing has to happen. So there is an inlet A and there is an inlet B. So these two will mix and exit through the form. So type A is called a main channel and this is called a side channel. So there can also be another possibility of there is a main channel and there are multiple channels. So if you can see here, the velocity is not a constant. It's not a constant, but it's a function of time, sine omega t, which means the velocity will be varying periodically. So if such a fluid comes, then we have to design it in a particular manner. So the multiple channel mixing happens from different channels and it exits. Similarly, the third type is 2 cross channels. So it's in the cross format. So it will come together like this and it may exit through these paths. So in the figure D, you can see that's a type of 2 mixing chambers. There are 2 barriers and there are 2 pneumatic chambers also. Okay, so pneumatic means the air pressure controlled. Okay. Then the fourth type, the figure E shows the Braille pin actuator. So that is actually like in sensing of, suppose for the blind, some kind of a blind people, if they need to detect the figures or something with the hand pressure, it can generate the kind of this actuation area. So there's a side channel, the fluid flow happens so that detection of the signal is possible for the blind people to help them. So this kind of micro mixers has got a huge amount of applications. Like even if in the case of a Braille pin, if there are multiple fluid, each corresponds to a particular signal or a particular hand pressure. So with the combination, we can obtain a number of outputs for a particular input. So that's the flexibility of these micro mixers. So you can see there's a stretching and folding. So there's a periodic signal generated and this will enable the periodic transversal flow through them. So these are all just an understanding of these micro mixers. So if the mechanisms of micro valves have been asked, so we should understand that generally there are different types of mechanisms, but generally there will be 3 types. One is magnetic force type, which is called as the magnetic actuation. Then the second type is light actuation. Third one is biology activation. So you can see 3 figures here. So magnetic force is like the first one here. So what happens? There is a cantilever beam, which means just a hanging beam. So this is the inlet through which the fluid enters. There is a bottom membrane here. So magnetic force is here. So as soon as it moves upward, it will lift the cantilever so that the fluid can enter and exit. Okay, so if the magnetic force is coming downwards, it can close the cantilever beam and the fluid entry is restricted. That's the first type. So this shows the top view of the magnetic type. I'm sorry, this is for the light actuation type. Sorry, this is for the light actuation type. So this is the top view and side view for the light actuation type. So you can see here there is a flow in. There is a PDMS device which is acting as a substrate. So you can see here there is a laser here. What happens? This NIR laser, the infrared laser, as soon as it strikes this, what happens? Yeah, the opening gets increased. The size of this gets changed and the flow can enter and exit through the space. So as soon as we switch off the laser, it comes to the initial position or the initial size. The third type is the biology actuation source, which involves, you can see here, a wallworks or some kind of a biological activated body. So in the presence of an LED, you can see here when it is kept on the right side, that thing will be attracted to this space. So the flow can happen smoothly and exit through here. And on the other hand, if you are keeping it on here, then it will come and hit the other side. So the flow will be restricted. So these are the general kinds of microvalve mechanisms. So if we look at the microfluidic valves, there are two main types. One is active microfluidic. Then comes the passive. So these are the two main categories of microfluidic valves. So these active valves, what they do is they use external systems to control the actuators. So which means that they require a power source. So like if we know the case of that laser beam, so it's a power source. So they need the power source to control the actuators and operate. So some of the recent designs include the electromagnetically driven microvalves that we have shown, then the air-driven pressure or the pneumatic type. So that is the main category of this active microfluidic valves. So other active valve designs use energy from the dry fluid. So dry fluid is, suppose if a fluid flow is happening, so in case the fluid power can be extracted through some means so that the working fluid itself can provide the required energy to activate this microfluidic valve. So that is called as direct energy conversion systems, DECS. So what is happening is some from chemical to other mechanisms, the processes are happening. Like the energy conversion is maybe from chemical to the mechanical type. So that is another category of this active microfluidic valve. So understand that active microfluidic requires a kind of energy to operate. And in case of passive microfluidic valves, their condition is such that their operating state is determined by the fluid under control. So their operating state will be determined by the fluid under control. So they do not use any kind of external systems to provide power. Okay. So they do not require any kind of actuators to provide power. Most common passive microvalves like flap microvalves, membrane microvalves, and ball microvalves. Even we know the kind of another is a Tesla valve. Like it's a fluid flow regulating device, Tesla valve. It does not contain any kind of, it's a very interesting structure, Tesla valve. So it just contain a design or the arrangement inside a channel so that the flow can be regulated by the efficient design of the channel. So it does not require any power. So it was invented by Nikola Tesla. So they regulate the microfluidic flow. So even the passive microvalves, they can be roughly divided into passive microvalves with mechanical moving parts and with the non-mechanical moving parts also. So that are the two types of the passive microvalves. Okay, I hope that is clear. Another kind of pneumatic, the microfluidic valve, which is of interest, is the thermopneumatic type. Thermo means heat or heat source. Pneumatic relates to air pressure. So this is the figure of a thermopneumatic valve. So this was proposed by Takao et al. Which is suitable for the micro valve in the thermopneumatic channel, which is directly used in the integrated blood detection system. So like blood detection, so that is actually related to the heat or the thermos effect of the flow. So this was invented by Takao et al. To determine such state. So what is it? The principle is like a thermos pneumatic actuator, which will be separated from the driving cavity, and the thermal expansion cavity is proposed to reduce the direct heat transfer from the micro heater to the flow channel. So this is like a separated from the main flow channel, from the mainstream flow. Okay. So this is proposed to reduce the direct heat transfer affecting into the flow channel. So you can see here there is a valve seat here where the valve is regulated and there is a gap formed. There is a micro heater, there is a wire. So when electricity is supplied, it will heat, and this chamber will be heated up. This heated up chamber will be there. There's a silicon substrate here. So there will be a difference in the air density. Suppose if heat is given to a chamber like filled with air. So what happens? As soon as it receives heat, the density, which is the mass by volume, that increases because the volume of the air present inside the chamber is increasing. Because from the basics, we know that volume is proportional to the temperature. So as temperature increases, volume increases. So if you are closing the chamber, there will be pressure developed inside the chamber. So the fluid gas will be exerting pressure. It is like a piston arrangement. If the heat is given to the fluid, what will happen? The piston will start to move. So this is from the thermodynamics, first law of thermodynamics. We know heat given is equal to dq equal to du plus dw. So when heat is given to a system, it will be used in the storing the internal energy, and work done will be done by the system. The system is closed or no work is done on the system, all the heat is used up in increasing the internal energy. So internal energy means the function of temperature for an ideal gas. So when internal energy increases, temperature of the fluid is increased. So the chamber starts to heat up. So when the volume is temperature increases, volume increases. So what happens? The air will start to enter into the pressure chamber, and it will try to press this valve seat and it will close. So if there is any flow happening, that will be restricted. And as soon as the electricity is switched off, the heating, the cooling happens of the fluid, and the pressure decreases, and the fluid that is present or the air that is present will return back to the chamber. So gradually the membrane will come to the initial position and it will be in open state. So that's a simple understanding of a thermopneumatic valve. So there is thermal effect, which is the heat effect, and this is the air pressure effect. So both are present in a thermopneumatic valve. So PDS membrane, which is the polydimethyl siloxane membrane, is used to realize large strokes or the large amount of performance is obtained using the PDS membrane. So that will be having better thermal expansion properties and all. So also it may be used as an adhesive layer between glass and silicon in the structure. So that is also useful. Okay. So that's all the discussion, just an understanding of a brief discussion of the week 8 lectures. So just we will quickly move on to some of the questions we will discuss. One question, which of the following is the example of active microvalve? It's the first question. First one is electro-osmotic, electrostatic, piezoelectric, all of the above. Okay. So what is osmosis? What is osmosis? Osmosis is actually the concentration driven flow, isn't it? So if I'm two fluid or same kind of fluid, which contains the solute and the solvent particles, and if they are separated by a semi-permeable membrane. What is a semi-permeable membrane? It will allow only the solvent particles to, specific particles to pass through the membrane. So if on side, if this is side A and this is side B, and if the concentration here is C2, and if the concentration of the solute here is C1, and if C2 is greater than C1, flow will happen through the semi-permeable membrane until C2 becomes equal to C1. So that is the equilibrium point. So electro-osmotic means this will be stimulated by an electricity. So it requires power. So active means require power source, isn't it? Yes. Passive, no power. So electro-osmotic is an answer. Is electrostatic is the case? Yes, electrostatic means we are providing electric charge to the plate or a capacitor. So this is like acting as a micro valve. So it will be regulating the flow. So we are providing electricity here also. So that specific particles will get attracted and the flow will be regulated. So electrostatic is it's also involving the electricity. So it's an active source. Piezoelectric. Piezoelectric is the effect of mechanical stress, which results in electricity production. And that electricity will be used to run the system. So that may be used to either to close or regulate any of the systems like electricity. If we need to generate electricity power, even in the previous case, if the heater is to be activated, we can generate the electricity by any of these sources. So that can also be an answer. So electroosmotic is correct, electrostatic is correct, piezoelectric is correct. So the correct option is all of the above. Okay. Next question. It's a problem. So a liquid enters a tube of diameter. So there's a tube and its diameter is 10 meters. And so I'll notate this 5 means showing the diameter. Okay. So diameter is 10 meters and the entering velocity is 20 meter per second. Density of the fluid is given as 100 kilogram per meter cube. Okay. The viscosity of the fluid is 20 kilogram per meter second. Please check the unit. So is the unit correct? Yes. Dynamic viscosity, the unit is Newton second per meter square. So Newton unit is kilogram meter per second square. So we are dividing it by meter square. So that becomes kilogram per meter per second square. Isn't it? Into second. So it will become kilogram meter per second. So the unit of dynamic viscosity is Newton second meter square. Newton unit is kilogram meter per second square SI unit into second by meter square. So that unit is correct. So please keep in mind that it can also be written as kilogram per meter second. So the question is, what will be the pattern of flow? Laminar, turbulent, transient, none of the above. So to find the pattern of flow, we require what? The Reynolds number. Okay. So what is the Reynolds number? Yes, Reynolds number is rho into V into D by mu. So what is the Reynolds number for this? Just substitute the values 100 into 20 into 10 by mu. So ensure that all of them are in SI unit. So the value is 1000. Reynolds number has got no unit. So we know that if Reynolds number is less than 2300 for a pipe, the flow is laminar. So our RE is 1000, which is less than 2300. So the answer is laminar. So if RE is lying between 2300 and 4000, then it is in the transition zone. If RE is greater than 4000, it will be turbulent or the chaotic flow. Okay, so the correct answer for this is laminar flow. I hope that is clear. In case if you have any problem in doubts or in the solving of problems, you can ask. We will post it in the chat box also. Okay. Next question. Glass microcapillaries are preferred over metallic electrodes because of the former. Okay. Option A, polarizes with the input current, does not have sustainable current carrying capacity, has less contact surface area, then has sustainable current carrying capacity. So question is, glass microelectrodes preferred over metallic electrodes. So the question is, which of the, why is it more preferred? So it should be an advantage. So option B is not correct. So polarizes with input current means it is going to disrupt the input channel, input signal. So if it is polarizing, it will create. Polarizing is the creation of opposite polarity on the charges on the signal. So that is going to disrupt the signal. So that cannot be an option. The third one is has less contact surface area. So we need to see whether it is having advantage when it has a less contact surface area. The fourth option is as sustainable current carrying capacity. So our observation will be on these two options. So contact area cannot be said for glass or metallic because both are a part of, we can manufacture both types with the surface area. That is only depend upon the diameter or the height of the channel. So this cannot be an option. It's not an advantage. So only possible option is it has got a high current carrying capacity. So the glass will be having, they can withstand sustainable over a longer period of time. While metallic electrodes may enter into charging or the polarizing effect. So that cannot be used. So the correct or the possible best option is a sustainable current carrying capacity. Okay. Next question, the fluid will rise in capillary when the capillary is placed in fluid if first option, the adhesion force between molecules of the fluid and tube is less than the cohesion between the liquid molecules. Next option, adhesion force between molecules of the fluid and tube is more than the cohesion between the liquid molecules. Third, the adhesion force between molecules of fluid and tube is equal to the cohesion between the liquid molecules. And option D, none of the above. Okay. So the question is, there is a capillary tube. And suppose if a liquid is placed, it will start to rise inside. So we know that two forces are there. One is adhesive force, then cohesive force. Okay. Adhesive is between different. You can remember this as different. Cohesive means of the same type. Means water molecule to water molecule. Adhesive may be water glass surface. So it is asking whether the capillary is to happen, which of the following should be there. So if the cohesive force between water and glass, adhesive force between water and glass is there, so the water will start to stick to the surface. So maybe it not be water, is some other thing. So any fluid, if the adhesive force is more, it will start to stick to the surface. So there won't be any capillary rise, only just sticking to the surface will happen. So cohesive force cannot entertain this capillary rise. So adhesive force, adhesive force cannot entertain the capillary action. So cohesive force, or if the water to water interaction is more, what will happen? If the cohesive force is more, so please make a correction. I think so sometimes it may get confusing. Cohesive means fluid. So if the fluid are together stable, then there won't be any capillary rise. But due to the adhesive force, the fluid glass surface, even if you see a capillary rise, there is a contact angle getting formed here. Okay. So I think I made a mistake in adhesive and cohesive. So the water glass surface interaction should be proper. So that force should be there so that capillary rise happens. So adhesive force should be greater than cohesive. If the water molecules are very stable in sticking to each other, then there won't be any capillary rise. They will remain in the same position. You can think like that. But due to a cohesive force between the glass and the water, the capillary rise along the glass surface is happening. So there will be a limit up to which this will rise. So that can be determined like that can be determined as a function of sigma cos theta by rho GD. This is the capillary rise. How much? See, if the capillary is happening, it can't rise infinitely. Suppose if we look at, so in a, we know that there is a, suppose the height of the tube is L. So so water can't rise like this and infinitely and create a permanent fountain like this, isn't it? Suppose water is rising and it is again falling to the same tube bucket, and without any power there is a permanent fountain created. So that case is not happening. Why that is? Because due to the surface tension force. So there is a limit up to which it can rise. So there will be a, outside there will be air pressure. So there will be surface tension force which is created due to the cohesive forces. Then there will be weight of the liquid. So balancing all this, we will get the capillary rise to be 4 sigma cos theta by rho GD. So for a given diameter of the tube, there will be a particular capillary rise. Theta is the angle of contact. Suppose if this is the meniscus of the water column, this will be the angle of contact which it makes with the glass surface. So that's the capillary rise. So our correct option for this question is the adhesion force between the molecules of the fluid and tube is more than the cohesion between the liquid and molecule. So be careful when using this adhesion and cohesion. Adhesion is like, you can remember another to remember is like our fevistick or fevikwik. It will be written as adhesive, which means between the gum and the surface. So this is with two different surface. So cohesion means with the same type. Okay, so correct option is option B. Next question, the stress strain relationship for Newtonian fluid is parabolic, hyperbolic, linear, inverse type. So Newtonian fluid is like where the shear stress is proportional to the shear strain. So if we draw a diagram like this with shear strain du by dy here and shear stress to be here, so we can write mu into du by dy. So that curve will be a linear type. So the shear stress and the strain. This is the velocity gradient. Okay. So velocity gradient, it will be a linear relationship. So what about the strain? Strain. What is strain? Strain is the change in the length. Okay. By original length, which is dimensionless. So if we look at this unit of this, meter per second by meter, so it is per second. So with the velocity gradient, it will be a linear curve. What about the stress strain relationship? So the change in original length by change in the length by original length is the strain. So how can we determine that? So strain is actually a function of if change in length by length. If we look into the strain equations or the equations of a deformation of a body from the basic solid mechanics, we know that shear stress by shear strain, if we notate it by gamma, that will be a constant called as the modulus, shear modulus. So shear stress is gamma into G, where gamma is the strain, shear strain. Okay. So what we need is the relationship between sigma and tau. So if sigma, the gamma is there, so it's proportional to gamma. G is the constant. So this can be assumed to be about stress strain relationship. So we know that tau equal to mu into du by dy. We substitute mu into du by dy is equal to gamma into G. Okay. So tau equal to mu into dy. So what is gamma? Gamma is mu into du by dy by G. Okay. So actually, when we plot this, there is no particular because gamma is mu, another constant k into velocity gradient. And tau is mu into velocity gradient. Okay. So if you divide tau by gamma, it will be a constant again. So that relationship will be a kind of linear. So understand that there is no information provided about G, this shear modulus. If the material is isotropic or kind of the same type only, this will be remain constant. So we can take that to be linear. So the correct option will be linear. I hope that is clear. The understanding is tau, we know it is mu into du by dy. And the ratio of shear stress to shear strain is Young's modulus. If you are assuming that to be a shear modulus, then if you are comparing them, that will be relationship will be a linear variation. Okay. Next question. It's a problem. Consider the steady two-dimensional velocity field that is given by v equal to u comma v, that is given by the function ij. So this can be represented like a vector in, it has got two components. This is the I cap. So this is the velocity in the x component. So ux, which will be 1.6 plus 1.8x. And there is a y component j cap. So u equal to 1.5 minus 1.8y j cap. So in a xy plane. So this is a two-dimensional flow case because there is no k component. So by the equation of continuity, we know that del dot u equal to 0 for what? For an incompressible 2D steady state flow. Okay, 2D is already given because we understand that this is a two-dimensional flow. Del dot u equal to 0, which means if u can be represented as in the question, uxi plus uyj. So del dot u means what? It is dou by dou x I cap plus dou by dou y j cap, the del operator, dot producting with ux I cap plus uy j cap. So just take the corresponding dot product. So what happens? Dou ux by dou x plus dou uy by dou y equal to 0. So this condition has to be satisfied. So let us check. We can differentiate ux with respect to x. So if you partially differentiate ux with respect to x, we will get 0 plus 1.8, and uy with respect to x, it will be 0 minus 1.8. So which will become 1.8 minus 1.8. So that is 0. So the continuity equation is satisfied. So you understand that this is for an incompressible flow. So if your assumption is correct, this equation is satisfied. Yes. This is an incompressible flow. So the answer is yes. This is incompressible flow. Okay, I hope that is clear. Next question. Somewhat a detailed understanding of this flow through a channel, micro channel with fluid. So first, let us read and understand about the question. So there are question is two immiscible liquids. Okay. Immiscible means they do not mix each other. So they are flowing steadily between two large parallel plates under the influence of an applied pressure. Suppose pressure is applied here. So this is plate upper and this is plate lower. Okay. So these liquid are flowing individually through a particular height. Suppose if we take this point as origin and if we assume this height as say h, this height also as h. So we'll take it as minus h because assuming it to be in the negative direction. Because in the question also they have given this convention minus 0.5 and minus 0.5 and the axis they have chosen x-axis along this direction and y-axis along this direction. So this will be plus y and this will be minus y. Okay. So the lower plate is fixed. So it can't move. While the upper one is pulled with a constant velocity of 10 meter per second. And the thickness h of each layer of fluid. So that is given to be 0.5 meter. This height for each fluid. So this will be liquid 1 and liquid 2. You can see the velocity profiles are different, but still they are a parabolic, kind of variation. Okay. So for liquid 1, the velocity profile is given, which is this profile. For liquid 2, the velocity profile is given, which is V2. Note that this is a function of y. This is also a function of y. A, B, C are constants. First objective is determine the value of constant A, B, and C. Okay. So we need to determine that. Then we need to obtain an expression for the viscosity ratio of the two liquids, mu1 by mu2. Okay. Then determine the forces and their directions exerted by the liquids on both plates if mu1 equal to 0.001 Pascal second, which is also Newton second per meter square. And each plate has a surface area of 4 meter square. So the surface area, so this can be like a channel, like a channel flow through which the fluid 1 and fluid 2 is passing. Okay. So it's not a micro level flow. This is like a, the thickness even itself is 0.5 meters. So it's not a micro level flow. So first we need to determine the values. Okay. So one important observation you should make here that at their interface, so this will be liquid 1, liquid 2. So at the interface, they will share the same profile. Otherwise, there will be slipping of the fluid. The flow will be disturbed. So we are assuming a smooth flow so that at the interface, they will be sharing the same parameters. So it is given here. Okay, so we are given velocity 1 at h equal to 10 meter per second. So which means velocity 1 of 0.5 is 10. So we can substitute that. So we will get 6 plus a into 0.5 minus 3 into 0.5 square, which is equal to 10. Okay. So if we solve that, we will get A to be 9.5. We don't know the unit, so we can dimensionally determine that. So just we need to obtain the value of A. Similarly, we know that the lower plate is fixed. Okay, so for the liquid 2 velocity profile, which contains the constants B and C, so we know that V2 of 0. Is it 0 or is it minus H? Yes, it is minus H, because here we are considering it in the negative direction. Here we are considering it in the positive direction. So that value is 0. Why is it 0? Because the lower plate is fixed. It can't move. So V2 of minus 0.5 is 0, which means that B plus C into minus 0.5 minus 9 into minus 0.5 the whole square is 0. So what is the value of B and C? So you can see that we will get an expression of B plus C, right? Isn't it? Isn't it? So we will getting an expression of B and C. So we need to determine B and C. So we need actually 3 conditions to support. So first condition, from the first condition we got A. We need one more condition. So what is that condition? Okay. So first we need to determine the I, as I said, at the interface they will be sharing the same velocity profile, right? So we got the velocity profile 1 because it contains only constant A, 6 plus 9.5 y minus 3y square. So what is the velocity at this point? Just substitute y equal to 0. So we will get V1 equal to 6 meter per second, which will be the same as of V2 at 0, isn't it? So from that, we will be getting the value of, suppose if we substitute that, we will be getting B equal to 6. So we got B. Now we have equation in B and C from the third condition, this condition. So the value of B, we will be getting how much? No, value of C will be getting to be 7.5. So finally, we can write the velocity profile V1 equal to 6 plus 9.5y minus 3y square, and V2 equal to 6 plus 7.5y minus 9y square. So this is the profile of the two. Okay, so note that this is a function of y. This is also a function of y, where y is the height above, vertical height. Okay, so we have got the velocity profile. Next, the task is very simple. So just we need to determine the viscosity ratio, mu1 by mu2. For that, what can we use? At the interface, the shear stress or the from the Newton's law of viscosity, that will be same at the interface, which means along this line at any point. Okay, which means that tau1, which is equal to mu1 into dv1 by dy at y equal to 0, which will be equal to mu2 into dv2 by dy at y equal to 0. So we will be getting mu1 into dv1 by dy will be coming to be 9.5 minus 6.5 at y equal to 0. If we substitute, we need to substitute y equal to 0. Then mu2 into 7.5 minus 18y at y equal to 0. That's why 0 need to substitute, which means that mu1 into 9.5 equal to mu2 into 7.5. So we will be getting the ratio mu1 by mu2 equal to 7.5 by 9.5. So it is equal to approximately 0.79. Okay, so the viscosity of liquid 1 to liquid 2 ratio is 0.79 nearly. So which hello? Any doubt? Okay, I think Tarini, your audio is any doubt? Okay. So we are getting the ratio of mu1 by mu2. So which means that mu1 is less than mu2. So which is more viscous liquid, because they are the ratio of viscosity. So we can have an understanding that mu1 is less than mu2. So liquid 2 is more viscous than liquid 1. So liquid 1 will be moving faster, or like it will be less viscous. Okay. Now we need to determine the velocity ratios. Okay. Not velocity ratio, the forces. So we got the shear stress. Shear stress is force by area. So what is for force? Is shear stress into area. So which means mu1 into dv1 by dy, force 1 on the upper plate. Okay. So on the upper plate, what will be the shear stress? At y equal to h, we need to, at y equal to h, we need to substitute. So for the upper plate, this is the value. So what is for the lower plate? What is the value? So into a is there. So it is y equal to minus h. So for the lower, which is f2, which is equal to mu2 into dv2 by dy at y equal to minus h into a. So what is a? It is given in the question as each plate has a surface area of 4 meters square. In the third part also it is given the liquid has both the constant mu. So mu value mu1 equal to mu2 is 0.001 Pascal second. So we can substitute that and we will get the value. So what is A? Okay, we have to substitute the 4 into value here also. So when we substitute that, we will be getting the value as 0.0835 newtons for the, I'm sorry, for the upper plate, the value will be 0.05 Newton. And for the lower plate, the value will be 0.0835 Newtons. Okay, so we are asked for the directions also. So when you substitute that, we are getting positive value, which means in the plus x direction. So this is right. And this also is to right, because we are getting the positive value, because we have taken x plus and this to be y plus and negative. We are getting it as negative, which means that it is to the opposite direction. So that's the understanding of the question. First, we need to obtain the constants for the profile from the given so-called boundary conditions or the end conditions. After that, we can determine the viscosity ratio using the interface condition, because at the interface, they will be having the same shear stress and the same velocity value. Then we need to determine the forces by multiplying it by area after getting the velocity profile. So as soon as we get the velocity profile, things are very simple. Just we need to determine, substitute and find the values. So this is another application. So he can see here there is no mixing of the fluid. If the mixing of the fluid happens, then there will be variation in the viscosity and the profile will be different from here. There is the profile will be a kind of a mixed type. So that will make our analysis more complicated. This is actually like given to be invisible. So generally in the questions, it will be the such kind of questions. I hope that is clear. If you have any questions, you can ask now. So that's all the question discussion for today. So I hope that you have gone through all the lectures. If not, you have to go through. So this BioMEMS course as such is like there's 8-week courses containing several lectures. So first one need to go through before attending the exam, NPTEL certificate exam. So regarding the exam, NPTEL exam, it's like it will be an online test. You may have paid and will be attending the test. So for that, almost approximately you have to you can come, the questions may come 40% at least from our assignments and quizzes, assignments or quizzes, then 60 around 30 to 40% and 40 to 50% may come from our video lectures. Then around 5 to 10% or 10 to 20% may come from our materials, reading materials suggested in the references. So the people who are going to attend the exam, they need to go through all these assignments, then the video lectures, then the other materials or essential references, so that you can successfully attend the exam very well. So that's all about the NPTEL certification exam. So I hope this course was this live session has benefited you to some extent by giving some of the practical solving, helping in solving your assignments or quizzes. So a feedback form is circulating in the our NPTEL SOM platform regarding our BioMEMS. So you can feel that how you feel about the course, whether it was helpful, which will be helpful to me also. And you can submit your feedback on that so that I will get a feedback on that. So that's all about the live interaction session. If you still have any questions or doubt, you can post in the discussion forums and clear the doubts or something in the previous. So all these live discussions are available in YouTube and content materials are there. In case if you have any clarification or doubt, you can always post that and it can be cleared. So personally, I wish you all the best for the exam, NPTEL exam. Prepare well and all the best. So if you have any questions, you can ask me now. Yeah. So I hope that there's no questions, and so that's all for the session today. And thank you. Wish you all the best, and thanks for your patient listening. Have a nice day. Thank you.